So in the context of light, we're talking about the law of reflection, or the bouncing law. And I promised then that when we discuss light being in a ray like this, just traveling in some direction, that of course if you look inside you'll see the photons or the waves, but we're not overly concerned with that. And there are some applications to astronomy with this, and here's our first one already, just with the law of reflection, sort of the bouncing law, straightforward as it is. It turns out that they're used in astronomy in something called retroreflectors. And here's what a retroreflector is. So what you would do then is you would sort of take a piece of material and another piece of material like this, and you would park them together, somehow fasten them together at right angles like this. So you put a 90-degree angle between them. Then what you do is you take your shiny material, maybe something like some mirror material, kind of like you might have in your bathroom, and you coat it on top of it like that. So essentially what you have are two 90-degree mirrors. That's what you have. So the question now then is, what happens when light comes into these two 90-degree mirrors? And let me give myself a little bit of room here, something like that. There we go. So what happens when light comes in? All right, well, we're talking about light rays. Let's just have one come in now. So here we go. Here comes a light ray like this, and it's going to hit the mirror right there. And so what's going to happen? Well, we know about the normal to the surface, which sort of exists right there. What will happen is the light ray will bounce out, observing the law of reflection. So this angle in here is supposed to be equal to that angle in there. Hope I've captured that. But now, of course, it bounces off the second 90-degree mirror down here. And so there's another normal in here, which looks like that. And here comes the light ray off of that normal like that, something like this. And so can you tell what a retroreflector does? Retro is the key word. Retroreflector. So you can tell that this is the light ray going in, and this is the one going out. So look at it and maybe see what you think a retroreflector does. Well, what a retroreflector does is sends ingoing light back out in the same direction. Goes back out in the same direction. So you might think, well, wait a minute, isn't that just a law of reflection? No, the law of reflection said that the angles rho is the same upon reflection, but this is literally sending a light ray out back in the same direction from when it came. So if it came in from the upper left here, like this, here it comes, it goes back to the upper left. So what have astronomers done with these things? Well, what they've done is they put some on the moon. So if here's the moon here, and everyone loves the moon, then put a retroreflector on the moon. And what does that allow us to do? Well, all the way over here on the Earth, we can shoot a laser beam at the moon. Not a very powerful one, well, relatively speaking. It'll go up, it'll go up, it'll go up, go up, go up, go up, go up, it'll go bang, it'll hit that retroreflector on the moon, go do its usual thing, bang, bang, and come back again. See how useful that is? So this is the outgoing beam, this is the ingoing one, this is the one going out. Well, let me keep the same names that I drew in the top. This is the ingoing laser beam that's going into the retroreflector, and this is the one that came out of the retroreflector. And you see it just goes right back to Earth. So what this allows astronomers to do is measure this distance here very precisely here. They can measure the distance to the moon to, I believe, just some resolution of centimeters or something like that. So measure the Earth-Moon distance. So the Earth-Moon distance, some ungodly precision, like centimeters, and that's one way they measure the Earth-Moon distance. Here are the actual retroreflectors. There it is right there on the moon, and there's another sort of farther view of it right here. This is actually what they look like. You can buy them for other things other than just doing astronomy and things like that. Maybe you need one in the lab where you need a laser beam to go back exactly in the direction it came from. And this is sort of a bad internet graphic of what I tried to draw, but here's basically that light ray going in, does its bounces, and comes right back out in the same direction. So those are on the moon, and they've measured the Earth-Moon distance that way. And it turns out, sadly, that the moon, oops, too thick, way too thick. The sad thing about it is the moon is moving away from us. Very slowly, but it is creeping away from us. So that at the moment then is what we need to know about the law of reflection. So I will go on next to the law of refraction. One last thing on the retroreflectors from the last video. We discussed that there's a retroreflector on the moon. Here's the Earth. And what scientists are able to do is send a beam up to the moon, the retroreflector, and it goes bang, bang, and comes back out again. And I mentioned that from this, they're able to calculate the distance to the moon. And how do they do that? Well, what they do is essentially the raw data that they get from this is they time how long it takes light to travel out and back. It's just a timing measurement. So right here, when they launch the laser beam, they sort of say go, and maybe they start a timer like 0, 1, 2, that kind of thing. Then right here, when the beam comes back, then they say stop, and they just sort of read the time off of that. That's how long it took light, believe it or not, to travel all the way out to the moon and come back. And so to calculate the distance to the moon then, as you might know this, that distance is basically equal to rate times time. And so the distance to the moon would be the rate that light travels, with some corrections in there that we don't need to worry about. But it's basically 186,000 miles per second. That's the number we remember from before. And they just multiply that by this time that they get from sort of the go and the stop up there. And so that's how they would actually calculate the moon's distance from the time. So it's very common to do distance measurements using time, and this is one example of it.